Right. Hi, Andrew. And so what we're going to do this lesson is we're hopefully going to get through all of those. We may not get through to aldehydes and ketones, but I certainly want to look at the reactions of haloalkanes, alcohols, and amines that you need to know. So just as a revision from what we did last week, because it's going to apply this week as well, is Markovnikov and Zaitsev's rule. As you only really do Zaitsev for the haloalkanes and the alcohols, but in case you get confused with the Markovnikov, it's related to addition. And what it basically says is the rich gets richer, so the carbon of the double bond that has the most number of hydrogens gets the extra incoming hydrogen. So if I've got that, I've got the red carbon and the blue and the yellow carbon. What's going to happen? The yellow carbon has got the most number of hydrogens, so that is going to get the incoming hydrogen, and there you can see it's gone from 2 to 3. That'll be the major product, and then you will get some of the other reaction where it goes the other way, and that'll be the minor reaction, or minor product, sorry. The Zaitsev is to do with elimination, and as I said, one way that you don't get muddled is you think of A and M go together, and they come earlier in the alphabet than E and Z. So A is before E, M is before Z, to help you work out which one's which. And then here for elimination, you look for your functional group, so it's either the alcohol or the halogen. Then you look at the adjacent carbons, and you see which one has got the least number of hydrogen atoms. So our functional group is on the red carbon, so you've got to look at the blue carbon and the yellow carbon to see which one has got the least number of hydrogens. And I think you can see it's blue, so that is going to get it, and that will be our major product because it's one of those hydrogens that go from the blue, so it's got one less hydrogen, and our minor product is where it's gone the other way. Okay, and then just I'm going to keep on hammering the reaction conditions. Please, when you go through these booklets and you make your own notes, look at those reaction conditions because they sometimes look very similar, but they're still different. So here we've got our first functional group, the haloalkanes, and we're going to look at their reactions. And if you think of those tips we did, remember the 7 tips. The first one was reactions were slow for organic chemistry and that we needed special glassware. And then we had things like look for the reactive center, look for the leaving group, look at the reaction conditions. What type of reaction is it? Is it substitution, elimination? And that will help you work out the products a lot more easily. So with a haloalkane, what I've got is a carbon that's slightly positive because the fluorine, the chlorine, the bromine are all a little bit more electronegative than the carbon, which means I'm going to have something that's a nucleophile attacking. So nucleophile, positive loving. So is OH minus positive loving? Will it be attracted to something positive? Yes, correct. So anything that's electron rich can be a nucleophile. So what we've got here is, say we've got propane, and my bromine group is more electronegative, so it's more negative. My carbon attached to it is more positive. My OH minus there is a negative charge, so it's electron rich. It's going to get attracted to something that's poor in electrons. And my leaving group, can you see that bromine is leaving with the electrons, is bromide. Now bromide is a neutral anion, so it's a good leaving group. That was one of those 7 tips I said look at. And because it's a good leaving group, it doesn't mind leaving. It doesn't want to try and hang on and get back in the game. So I can replace my bromine with an OH. And so it's a substitution reaction. Haloalkanes can also do elimination. So with elimination, there's my bromopropane again. And what's going to happen, my OH, so you can see I've got OH in both cases. One, though, is aqueous, so the water supplies more OH. Okay, I've got a rich supply of OH, as a nucleophile to come in. What I do here is it's an alcoholic solution, so I've removed the water because all I want to do is an OH to take away something that's not very reactive at all. So I need stronger conditions because a CH bond is quite a strong bond, and what's happening, it wants to take that hydrogen proton away, and then the electrons in that bond go and get shared between the two carbon atoms because the bromide gets removed with its electrons. So I've still got that good leaving group, but I don't want lots of aqueous OH minus because I'm trying to remove something that's a lot more difficult to remove. So it's harsher conditions, and I get an alkene. So I do have OH minus as my nucleophile in both cases. We don't really talk about a nucleophile here because it's not incoming. It's just simply a base. So here we talk about as a nucleophile, loving a positive. Here you'll notice it's simply acting as a base, removing a hydrogen proton. It's not coming in, it's not loving a positive area, as you know, it's not coming in over there, it's grabbing a hydrogen H+. So here it's acting as a base, up there it's a nucleophile. Is that clear between a substitution reaction and an elimination reaction? Good. Now, does Zaitsev apply in this specific reaction I'm showing here? Because remember, whenever you do elimination, you've got to think of Zaitsev. Now, will it apply here? In this specific case, it won't, simply because my base can only take one of these two hydrogens. It will not take from there, and I don't have another choice. Because remember, I said you look for your functional group, so it's a bromine on this carbon, and then you look at adjacent carbons. Now here's an adjacent carbon. Adjacent means next to, but there's none on this side. So there's no choice for the base to attack. The base will only attack from one side because that's all what's available. So we don't get major or minor products here because we didn't have any choice to go one way or the other. So you'll only get perhaps Zaitsev rule applying if it's a secondary haloalkane, and only then if the molecule is asymmetrical. If it's symmetrical secondary haloalkane, then again it doesn't matter which side it attacks because both sides are identical. If it's a terminal or a primary haloalkane, then it can only go from one side, so there's no major or minor product either. Okay, so, and again I said they're the reaction conditions. Now with this one, I just want to get going very quickly. Here he's making up a solution of the KOH and the ethanol, and I'm going to just move it on. He's going to then set it up. Sorry, he does. Okay, there he's got his chloropropane with the KOH, and he's heating it. And then I'm just going to move it on quickly. You can see a gas is being formed, and I'm going to ask those questions about what's a liquid, what's a gas. And he's going to at 2.55, so a little bit further on. Right, he's now adding bromine to that product. So he's collected the gas and he's adding bromine water to it. What is happening to that brown color? Is it gone? Yep. So it's decolorized the bromine. So think of what test that is. And then he's doing a final test over here. He's taking a match. Oh, sorry, there the match went. It's right at the end. And did you notice it just went out straight away? So I'll just leave it because that's a bit more interesting than that. So just thinking of that, first of all we had a liquid. That chloropropane, 2-chloro-2-methylpropane, was a liquid. Why would it be a liquid and not a gas? This is going back to the 305.1 that we did when we looked at physical properties. Okay, because yes, it's got a higher molecular mass, and remember, the higher the molecular mass, the stronger the temporary dipole forces of attraction, and so the higher the boiling point. And so it's the haloalkane is a liquid. We're changing it into a alkene or an alkene. So we've lost the heavy chlorine. So can you see we've got an alkene? It's pretty much non-polar. It's considered to be non-polar. Can you see why that is a gas? So always think of your physical properties when you're doing these reactions. Now, the bromine was decolorized. Why did that brown color disappear? Okay, the double bond. It's one way of testing a carbon-carbon double bond. As I said, bromine will react with anything, but slowly. But with an alkene, it's very quick. And then the final thing, by lighting the match, I did say it went out very quickly, but it burnt, so that's why I did it over here. It's very quick, it's at the end. You can see there's that flash of light and then it's gone. And that's because alkenes are flammable. So haloalkanes are not flammable, but alkenes are flammable. So it's just one of the properties from level 2, but you might need them again at level 3, because they do say they expect your knowledge of level 2 to be used for level 3. Right, so the reactions of the haloalkanes, remember we had 4 reactions for the alkenes, there's 4 reactions for the alkanes, so it makes it easy to remember. We've done the one about the elimination, but let's start with the amine. In this case, it's a substitution reaction. So I'm trying to find my cursor. The substitution reaction, there's my nucleophile. And it's in alcoholic conditions because I want just my NH3 to add on. I don't want any aqueous hydroxide sitting around. So that will add on, kick out the bromine or the halogen to form an amine. If I use a primary amine as my nucleophile, I can get secondary amines. If I want to convert to an alcohol, I use that aqueous OH. So there's my nucleophile, aqueous OH. And if I want to eliminate, I use alcoholic OH. So all of them are alcoholic, except for the forming the alcohol. So that's one way to remember. If you want to make an alcohol, you don't use alcoholic reagents or solvents. You use an aqueous one. It just simply increases the supply of the OH minus from the water. Okay, so let's match them very quickly. If I want to form alcohols from haloalkanes, you just look for the aqueous one. Okay, so there it is. If I want to form primary amines, what do I use? Okay, you can see it. Okay, the conch, yep, the conch NH3. So all of them are fairly concentrated. In the standard, it talks about conch NH3. I've added the alcoholic because it is alcoholic conditions, and I have noticed last year's paper they spoke about alcoholic. So it's good to know it is either alcoholic ammonia or concentrated ammonia. And then secondary amines is when I react the haloalkane with a primary amine, and an alkene is an alcoholic OH. Then just as a question, you know, I've always said you only have aqueous forming alcohols, is we just want to get a purer product, because remember, if I take ammonia and I dissolve it in water, I do form OH minus. So even though it's concentrated ammonia, if I have any OH minus around, that could also act as a nucleophile, and it just means I get a messier reaction. An alcohol is not as good a nucleophile as OH minus. Right, and that works with the primary amine as well. So we've done haloalkanes. Remember, it was 4 reactions, and it was pretty much substitution and elimination. So those were the 2 types of reactions. Alcohols have got 3 types, 3 types actually. We've got the substitution and the elimination, and then we've also got an oxidation. So We'll just have a little bit more now. But otherwise, it's the same thing. I've got an electronegative oxygen taking electron density from the carbon, making it slightly positive, which means I'm going to have nucleophiles attacking. So if there's my slightly positive carbon attached to the hydroxyl group, here's a nucleophile SO2, and it's going to attack the positive carbon or slightly positive carbon, and my OH is going to come off as OH minus. What will happen is actually if this chlorine adds on like that, so we've replaced the OH with the chlorine, I'm left with pretty much OH and then a ClSO, and it just does a little thing in this mixture, and those atoms, OH, ClSO, form SO2. So if you like, this S and O grabs that oxygen and forms SO2 gas, and then I've got the Cl from here and the H. So we have quite an acidic medium at the end when we use SOCl2. Right, now alcohols also differ from haloalkanes because we actually have got two reactive centers. The carbon being positive, so that is being attacked by nucleophiles, but we also have the oxygen, which is electron rich. And chlorine doesn't like sharing electrons, it cannot form two bonds. Oxygen can. So oxygen can act as a nucleophile. So you'll do this in the next lesson, but what we've got here is really my OH acting as a nucleophile to a carboxylic acid that's also quite positive, and it kicks out this OH. And what we land up with is the ester. So when we did the naming of esters, remember I said there's that bit from the carboxylic acid and there's that bit from the alcohol, and A before C, carboxylic acid before, the alcohol before the carboxylic acid. Do you remember that when we did naming? Or was that too long ago? Okay, right. You remember. Good. Okay. So we'll do that reaction again in detail in the next lesson, but that's just to show there are actually two parts to alcohols, because my OH can also react, not just my carbon. And so there I'm just showing what's coming off. I've got an OH from there and an H from the alcohol, and so I have got a good neutral leaving group of water. And the conc H2SO4 is the reagent. It's not really taught in our curriculum, in any of the standards, but concentrated sulfuric acid is a very good dehydrating agent. A fun reaction is if you take concentrated sulfuric acid and you put it on sugar, and you'll find that you can look it up on YouTube. What it does, because sugar has got a lot of OH groups, it just simply strips the sugar of all those OH groups, and you're left with this black carbon mass, and it all bubbles all over because it's a very exothermic reaction. And as it strips off the water turns into steam, so it looks like a real witch's brew. Okay, now what I just quickly want to show in this one, this top one is it's 26 minutes, it's really long and slow. Watch it when you're having lunch one day. Okay, it's does explain things very clearly though, each of the steps. So if you're looking at the recording, it's Frankly Chemistry, and that's the name of that video. This one down here is a little bit quicker, and what we're going to do here is I'm just going to move it on to, come on. Yeah, so what we're doing there is we adding the alcohol, and we also, well, in this particular case we aren't adding the alcohol there. I'll just stop it here so you can see what's happening. We want to add HBr to make the Br add on, but HBr is a very dangerous chemical, so you make it in the mixture, and so that's what these first two reagents are. Sodium bromide and concentrated sulfuric acid is to make the HBr, and that's done in an ice bath, so you don't get it going all over the place. And then you add your alcohol. So I'm going to move it on now to about here. There it is. Can you see it's in the ice bath? And that's when we're making the HBr. And now I move it on. So there I'm distilling it now. So I'm now making the haloalkane. And the haloalkane, because it can't do hydrogen bonding, it has got a lower melting point than the alcohol, even though it'll have stronger temporary dipole force of attraction because of the heavy bromine. And then I'll move it on. Sorry. My cursor keeps on going and disappearing again. There, got it back. And I'll move it to 3. Right. So there we're adding water, and that's just simply to dilute all that acid that we've added. And then we add the bicarb. So I'm just going to, at 4 minutes. Okay, so there we're adding the bicarb. That's to absorb all that acid, that HBr, the acid we made, the sulfuric acid. It's to neutralize it. So this is a sort of a good reaction. That sodium chloride is just simply to make sure that as much organic product comes out of the solution as possible. So I'm just going through the reaction procedure because I did notice last year they asked quite a bit on reaction procedure, so it's quite good to know about that. So you can look at that again if you want to. Right, these I'm going to look at because it's quite good to see how it reacts with thionyl chloride. So this first one is, and I'm going to move it straight on to one. Okay, so what they've got there is thionyl chloride in one test tube, and then they've got the alcohol in the other test tube, and now they're adding one to the other. And notice the bubbling when it gets added. And can you see it's because we're making gases, SO2 gas and HCl gas. And he's going to test it now with ammonia, and you can always know if you've got HCl is if you form that white smoke. So that's what that's for. And this one down, okay, now he's going to test for the SO2. It's a redox reaction. You know SO2 will be oxidized by permanganate, and so you'll see the purple color disappears. So that's what he's doing there. I'm not going to look at this bottom one, but this is pretty much the same sort of thing, but he's also using PCl5. You have to learn SOCl2, PCl5, and as some of your reagents. This is just how to make an ester, and the important bit over here is really the fact that we reflux and distill. So what we just, I'll just stop it there. Think of that as your carboxylic acid. It's a form of carboxylic acid, and there's your sulfuric acid, remember your reagent, and then your alcohol. Now you basically react that, distill it, and then you take your distillate and you have to wash it with bicarb because some acid could have gone over. And that's why you want to neutralize the acid. So if I just move it on, there, okay, it's first in the ice bath when we're making things in situ, and now we are going to start heating it. I've missed a bit. There should be a distillation, but as I said, I don't want, you can watch these in your own time because they're just another YouTube clip. Okay. Right. Alcohols with elimination. So we've done the substitution either from the oxygen or where the carbon gets substituted, but you can also have it eliminated. And so I look for my functional group. It's on this carbon over here, the red one. So is the hydrogen going to come from the blue carbon atom or from the yellow carbon atom? The yellow one, because the poor get poorer, the yellow one's got fewer hydrogens, so it's going to come from there. And remember, reaction conditions for alcohols is concentrated sulfuric acid, because it's a dehydrating agent. I'm removing water. With the haloalkanes, it was actually OH minus. It was the opposite. It was like a base. Here it's the acid, because it's a strong dehydrating agent, because we're removing water. So there we've done it, and you'll notice it came from the yellow one as our major product. We will get some terminal alkene as our major product, as our minor product as well, where it forms between the red and the blue. Okay, here this also shows the whole procedure. Okay, you've got to go. I'll just carry on, and then I'll see you hopefully tomorrow. Right, I hope the dentist goes well. Bye. Right, so let's carry on. You can look at this YouTube clip in your own time, so over lunch or something, so you can see the procedure. You'll notice that the procedures are all very similar for organic chemistry. So, with the alcohols, we've looked at the substitution, we've looked at elimination, and now we're looking at oxidation. So, again, the oxidation, we look at the reactive center, this carbon containing the OH, and we look at what else is on that carbon. If it has a hydrogen attached, as in this case, sorry, my cursor's disappeared, there it is. If it has a hydrogen attached, then that carbon can be oxidized. Now, in organic chemistry, we don't really worry too much about oxidation numbers and so on. We see oxidation as removing hydrogens or adding oxidants. So there's the hydrogen I'm going to remove, and I treat it with a strong oxidizing agent like permanganate or dichromate, and I will get a carbonyl group. So I remove pretty much this hydrogen and that hydrogen up there, and I form a double bond. So that is the oxidation, where I take a secondary alcohol to form a ketone. And there it is. If I have a primary alcohol, so there I've got it on the end carbon. The primary, it means, remember, is that carbon is only attached to one other carbon. Here this is secondary because it's attached to two other carbons. So now my primary has got two hydrogens. There are my two blue hydrogens. So it can actually be oxidized twice. So I can take it, treat it with dichromate, and remove one of those hydrogens. And if I continue to heat it, then, or react the aldehyde, I can oxidize it all the way to the carboxylic acid. So I've now, if you can see, I've added another oxygen. Now notice the difference between a secondary ketone and a primary, so secondary alcohol and a primary alcohol. In a secondary alcohol, I reflux because all I can do is a ketone. I can't do it further. If I wanted to have a primary alcohol and stop it at this stage, at the aldehyde, and not go further, then I have to distill it while the reaction is happening. So while it's happening, then my aldehyde, which has a lower boiling point, because it doesn't have the hydrogen bonding that the alcohol has, so it has a lower boiling point, I can boil it off, I can distill it off while the alcohol still stays behind, any unreacted alcohol, and gets oxidized to the aldehyde. So if I wanted to go all the way straight through to the carboxylic acid, all I would do is I take my dichromate, but I just simply reflux it. The same thing as up here. I just reflux it, and any aldehyde I make just carries on being oxidized to form the carboxylic acid. So remember that carbon has got a hydrogen attached, which can also be removed, and that's why it can be oxidized further. Ketone doesn't have a hydrogen attached, so it can't be oxidized further. What about a tertiary alcohol? Do you think a tertiary alcohol would be able to be oxidized? Think of it, does the carbon to which the alcohol is attached have a hydrogen? If you think of it, carbon can only have 4 bonds. If one's to an OH and 3 are to carbons, there's no bond left to a hydrogen. So a tertiary alcohol cannot be oxidized further. Now here are some YouTube clips all showing similar things where I'm oxidizing. So I'll just take one of these. Okay, I'll just take this one, and I'm going to just move it further along. So can you see that orange color of the dichromate? Because this is one of your tests. If you treat something with orange dichromate and it turns green, then you have an alcohol, because an alcohol can be oxidized. And if I carry on, sorry, these things always disappear on me, there you can see it's starting to turn green. And you can watch it, and you can see it under the reflux condition. So there you're refluxing it. It means it goes straight up, condenses, and drops back down again. That means you're going to be making the carboxylic acid if it's from a primary alcohol. If you want to distill or remove the product as it's being formed, so you get the aldehyde, then you'd have to distill it, and you can watch this one over here. Okay, so what reagent is needed for the following reactions? So it helps to keep on writing these down, write them out as often as you can so that you remember. So if I want to go from a primary alcohol to an aldehyde, remember an aldehyde can be oxidized, so I've got to stop that oxidation before it happens. So I need to distill it. I need to remove that aldehyde before it can carry on oxidizing. If I want to go from alcohol to an alkene, I am removing water. I'm dehydrating it. So I need a good dehydrating agent, concentrated sulfuric acid. If I want to go from an alcohol to an ester, remember an ester is made up of an alcohol and a carboxylic acid. So I need to look for carboxylic acid. And because I'm removing water in that reaction, I've got concentrated sulfuric acid. If I'm going from an OH to a haloalkane, if it's a chloride, I'd use SOCl2. That's a great one to use. Otherwise, there are other ones, as I mentioned, PCl3, PCl5. Then this is going from a primary alcohol to a carboxylic acid, and in both cases I just simply reflux them, and I can use either permanganate or dichromate. Note that all of these have been acidified, so you get that good color change. And then if I want to go to a ketone, it's the same sort of thing. I can reflux. I don't have to worry about removing my product. Okay, so we've done haloalkanes. We saw there were 4 reactions, just substitution or elimination. Then we did alcohols, and we saw, actually I didn't count the reactions, but we saw that you had substitution reactions, you had elimination reactions, and you had oxidation reactions. You could oxidize them. You also had the OH of an alcohol that was able to react. Let's look now at the amines. Now amines are bases, so they'll be doing acid-base reactions. They also can be involved in being replaced by something else or acting as a nucleophile. So we're going to be using them acting as a nucleophile and as a base. So there's my primary amine, and I'm just treating it with acid, the same like ammonia. And can you see a base is a proton acceptor? Can you see I've accepted another proton? So this animal is not a dog, it is a salt, ammonium salt, but it's the organic ones. So this would be ethyl ammonium, and then whatever the other part of the salt is, ethyl ammonium chloride, or so on. So that is a straightforward acid-base reaction. Never forget that. It's a great test to use to work out if you've got an amine. Does it react with an acid, or does it turn litmus paper blue? So it's ethyl ammonium ion, or the latest IU pack is ethanaminium ion. So it's ammonium has 2 M's, aminium has got 1 M. So just to be aware of that. So that was where it's reacting as a base. Now we're looking at it as a substitution reaction, that type. And we're going to look at it not so much as anything substituting onto the carbon, because this carbon isn't that positive, because nitrogen doesn't mind sharing its electrons. It might be actually quite electronegative, but it doesn't mind sharing its electrons. So nucleophiles don't attack an amine as much. But an amine is a brilliant nucleophile in itself, like that OH we saw. So though that lone pair of electrons in the nitrogen will attack any carbon that is slightly positive, like in a haloalkane. We've got a good leaving group there. In this case, it's the chloride. And so there I've got my amine compound added on to my haloalkane. So that came from the haloalkane. And it can carry on until I've got no more space left on the nitrogen. And can you see I've now formed a tertiary amine over there. So in each case I've been attacking and I've been adding on. So that carbon of my haloalkane has added on, and it keeps on adding on. So that is your substitution reaction that you have to know. Now I've said there, when you've finished reacting this, you always add bicarb to the mixture afterwards. And if you think of why, well, think of what your leaving group is. It's the chloride or the halogen, the halide, plus, of course, you've got one of the hydrogen atoms coming off the amine bit. So you notice here this amine has got 2 hydrogens. Now it's gone down to 1, because nitrogen only prefers 3 unless it's acting as a base, 3 bonds. There's the 3 bonds. So each time I'm removing an H and a Cl, or H and a Br, and I hope you know that HCl is acidic, so I have to neutralize that when I work up my product. Okay, so let's look at this practice example. We've looked at things like reagents, we've looked at products. A good way of also remembering your reactions is to think of what can I start off to form this product. So if I form an alcohol, what would my starting material be? And if it's KOH aqueous, remember that means I've got lots of OH minus that can attack, and so it'll come from the haloalkane because I've got lots of nucleophile to attack and remove the bromine. If I want to make an amine and it's alcoholic, then it's also a haloalkane. Now that could have been a chloride, okay? This could have been a bromide, it doesn't really matter. Why have I made the bromine attack on there, attached to this carbon, whereas I made the chloride attached to this first carbon? It's all to do with where my position is of my compound, of the functional group in my final compound. So here my OH is on the second or the middle carbon, so I've got to have my bromine on that middle carbon, because the nucleophile is going to attack that carbon atom. So it has to add on to the middle one to form a middle, a secondary alcohol. Here my amine is primary, it's on the end carbon, so I have to have my Cl, my leaving group, on that end carbon. Here my Cl is on the middle carbon, but I'm forming it. So if I use HCl, that is what I add from an alkene. Okay, I don't use HCl on an alcohol, I use it from an alkene. And In this case, remember, if it's adding on, it follows Markovnikov's rule. So this would be my major product, because the hydrogen would add onto here and the Cl would add onto there. Now I want to form a ketone, and it's oxidizing conditions, so I have a secondary alcohol to do that. Right, let's look at the aldehydes. Aldehydes pretty much just go oxidation or reduction. So just as a recap again, alkenes were pretty much addition and elimination. Well, eliminations to make alkenes. There were 4 reactions we looked at there, because there were 4 types of addition reactions. Then we looked at haloalkanes. We had 4 reactions there. 3 of them were substitution and 1 was an elimination. Then we looked at alcohols, and we saw that there were elimination, substitution, as well as oxidation reactions. Now for aldehydes and ketones, which we'll do, aldehydes have got oxidation and reduction, and ketones only have got reduction. So let's look at aldehydes first. Aldehydes, remember, there's this whole thing is my functional group, but this is the carbon of the functional group, and it has got 1 hydrogen there that can be removed. So it can be oxidized further with a good strong oxidizing agent like dichromate or permanganate, and there I form the carboxylic acid. So because it's got that hydrogen attached to the carbonyl, I can oxidize it. So think of it, can I oxidize ketones? Because we had said that before, remember we can't. Now if we use dichromate, remember we can also use this as a test for aldehydes or as a test for alcohols. What color change would you see? If I'm using dichromate, dichromate is orange, and when it's all been reduced, then it forms a green chromium ion. This is colorless, the aldehyde. The carboxylic acid is colorless, so there's no change there. So it's just my orange dichromate acidified. It has to be acidified to make this color change to go to a green Cr3+ ion. If you were making the carboxylic acid, what test would you be able to do to test it? Those videos that we had before are really good. They show all these different tests. You can use litmus paper. You can treat it with bicarb, because you know that an acid plus a carbonate will form carbon dioxide bubbles. So if you see gas being evolved, it turns lime water milky, then you know you've got a carboxylic acid. Right, aldehydes can also be reduced. So there's my active or my reactive center, the red carbon of that carbonyl group. And just like I could remove an H, I can add an H to form the alcohol again. And what we use here is sodium borohydride. It's a reducing agent. So the hydride is H- form, so it's rich in electrons, so it will add on to the carbonyl. Okay, and you always get a primary alcohol and not a secondary or tertiary, because obviously the aldehyde is at the end of a chain, so I'm always adding on to a carbon at the end, so it can only be a primary. Ketones. Ketones don't have very many reactions at all. They just basically get reduced. If you go and study further, you'll see there are other ones, but as far as you're concerned, they only get reduced. You can't oxidize them, you don't substitute them. All you do is you reduce them. And that's basically your carbon of the carbonyl can have a hydride attacking it, so it reduces it, and there it's added on. Carbon can only form 4 bonds, so if something is adding on here, the double bond has to break. And again, being a ketone, you always get a secondary alcohol, because the carbon always has to be in the middle, be attached to 2 other carbon atoms to be a ketone, and so your alcohol will always be secondary. Right, and then I think I've already explained why do ketones only undergo reduction, not oxidation, and that's because ketones don't have a hydrogen attached to the carbonyl, So there's nothing more to remove from that carbonyl carbon. Here are some other videos which hopefully are going to start coming up. Okay, I don't know why they haven't come up, but these are the different tests. I do want to, there they come. I'm not going to look at these very much, but you can see there's a color change you could use, a silver mirror test, which I'll do in the next slide, and the feelings test, which I'll also do in the next slide. But these are also other ones that are pretty good to watch yourselves. So these are the ones I want to show. So what we've got here is a silver mirror test, or the Tollens test, and these are testing for aldehydes. So what you do is you first make your Tollens reagent, which you don't have to know how to make it, so I'm going to skip that. And the important bit here is, oh, they're still making it there. You make it with silver. Right, now they're adding the Tollens reagent to my aldehyde down there. So you can see it's in 2 layers. So the aqueous layer is at the top, and what will, okay, well they're still adding it. Right, now we're going to be heating it, and hopefully, right there, they're putting it in. And as it gets heated, notice I'm getting also that bit of brown precipitate. That's that silver that is depositing as a black precipitate. And if you're lucky and you've cleaned your test tube nicely, then you'll have the silver also forming like a metal surface around. So it can either form as a clumpy metal at the bottom, or it could be just form as a surface. So that's what we call the silver mirror test, where the aldehyde gets oxidized by the silver ions, and the silver ions get reduced to the silver metal. So Tollens test or silver mirror test. The other one is the feelings test or the Benedict's test. They're pretty much the same thing. They work on copper ions, copper 1+ ion. The ingredients are slightly different, but the important bit is the color of the copper 2+. So I'm going to move it. Okay, right. I just want to. So there is your Benedict solution. It's based on the copper 2+. Now they're going to be putting in an aldehyde on the right-hand side, and I've forgotten what they put on the left-hand side, but it's a non-aldehyde. And when they add, okay, there they've added the feeling solution to both. Okay, you heat them. Notice all organic reactions need, I'll just move that back a bit. So they all need to be heated because organic reactions are slow, even if we're doing a bit of inorganic on them. Notice the color change happening in the one that's got the aldehyde, because the aldehyde is being oxidized by the copper 2+, and the copper 2+ is being reduced to copper 1+. And copper 1+, depending on what the salt is formed, but in this case it's with tartrate, it forms that brick red precipitate. This is saying glucose because glucose has got an aldehyde on it, so they've used glucose here. So those are the 2 tests you do need to know. Here are all the reactions. As I say, practice writing out the reagents, and also think of, if I've got an alkane, how do I get an alkane? It's from an alkene using the hydrogenation. So try and link as much as possible, so that you don't just think one way. Don't just think of alkene to alcohol, think of alcohol to alkene. Or just think of, if I've got concentrated sulfuric acid, what are all my reactions that I know so far that use concentrated sulfuric acid? Concentrated sulfuric acid by itself with heat is to go alcohol to alkene. Concentrated sulfuric acid with water is to go from alkene to alcohol. We've done concentrated sulfuric acid, and it's not showing here, but it's for carboxylic acid and alcohol to form an ester. And that's about it as far as those go. So just keep on adding, linking all your reagents together. So let's go and do a bit more practice. If I've got sodium borohydride and I want to form a secondary alcohol, I needed to have started with a ketone. So there's my ketone. If I've got an amine and I'm reacting it with a haloalkane, remember this acts as a nucleophile onto that carbon, so I'm going to form a secondary amine. You do not have to know the naming of secondary amines. So in the exam they'll ask you to draw the product, but they'll never ask you to name it. Here I'm using concentrated sulfuric acid and water to form an OH. So think of where that happened, and that was from an alkene. And then again SOCl2. When did I use SOCl2? From an alcohol to form an haloalkane. And that is the end of the lesson, and I will hopefully see you next time to do the last lot of the reactions. Goodbye.